Hi, welcome back to Advanced Algorithms. So this is the 10th session, and we just started talking about randomized algorithms and probability last time. So I introduced a whole lot of concepts from probability theory that we will, at some later point in the course, use to a certain extent, maybe not all very regularly, but a certain background is important, and I wanted to give you a collection of proper definitions that cover all the cases that we will need. Now, we've already talked about algorithms last time that can run on certain instances, certain bit strings forever. And I mentioned that most of the time we will actually not have to really deal with such cases and such algorithms, because we can avoid having algorithms that run forever. And today I want to be more precise what I mean by that, and also give you a first classification of randomized algorithms. So first of all, let's consider a general problem to compute some function. So we're given a function that just maps some strings to some other strings. This certainly covers the case of decision problems that we've talked about in the past whenever we were referring to lower bounds in complexity theory. So given the language, we set that function to be the characteristic function for that set, for that language. And then the definitions to follow also cover the decision problems. One could generalize this to allow random outcomes, where this function should be some relation, but then we also have to specify the probabilities and so on. So we will not include cases like our roll die example, where the outcome was a random number. But we will informally use such procedures for random generation of certain things as a building block for algorithms. So it's nevertheless a helpful exercise that we went through. But now here, for discussing problems and solutions to problems, we have deterministic functions. Now the first type of randomized algorithm is called Las Vegas algorithm. And that's one that never gives you a wrong answer. So A is an algorithm for every input x of the sigma star alphabet. For every such input, it returns a value, because it's supposed to compute this function. That value should be something in gamma star. But we allow the randomized algorithm to also return this question mark, which corresponds to I don't know. Something went wrong in my computation, and I decided to rather stop here. We'll talk about that in a second. The first requirement in turn says I always terminate after a finite number of steps. This might, of course, depend on the size of the input, how long the computation takes, as usual. But we explicitly exclude this case of infinite computations. So this is the great benefit of this definition. It says we never have to consider algorithms that run forever. We always compute either the correct result, or we say we don't know, and we give a guarantee that we won't say don't know all the time. Otherwise, such an algorithm would not be useful. Any such algorithm is called a Las Vegas algorithm for this problem f, for computing this function f. Now you might be a bit concerned about this don't care thing, and indeed there's a certain trade-off, in the sense that we can, given a Las Vegas algorithm A for a certain problem, we can generate another algorithm that always returns the correct answer and never says I don't know. We also get a guarantee on the bound, on the time that this algorithm spends, but this time we only get an expected time bound. And in fact, it's not possible in general to guarantee that this will be a a terminating algorithm. In general, you have to live with the fact that B now can run into infinite computations, which brings you back all the theoretical problems in dealing with these algorithms and computing probabilities and so on. But you get for sure the correct answer. And also on expectation, you don't lose so much time. And the second theorem here says that you can also go back in a constructive way. Whenever you have such an algorithm B, that's an outcome of this theorem in a sense. So it always computes the correct outcome, but you only have a bound on its time in terms of the expected time. Then you can compute from B a Las Vegas algorithm for F in the sense of the form of the definition we just had, which explicitly said that it has to terminate after a certain fixed number of steps. And we can even say what this bound will be, what it will be at most. But then A again can return the question mark, I don't know, but never more than half of the time. So we can trade expected time for worst case time bounds, but then we have to allow the don't know, and we can go back. Now both of these types of algorithms are called Las Vegas algorithms in the literature, just to make it a bit more confusing. The defining feature of Las Vegas algorithms is that they never return something wrong. Whenever they return something different from the correct answer, they tell you explicitly, I didn't find the result, I don't know. And this is the important part. Now these two theorems are relatively easy to prove, and I think you will find it constructive to do so in the exercises. Therefore, I leave this out. Let's look at a few examples. For the moment, just these two. First of all, our roll-die method. In the formal sense, I already mentioned it, it's not part of the framework because it's not computing a function. But let's assume that we accept the random size of the die as just a certain output for the function and ignore the function in a sense. Then our rejection sampling method is a Las Vegas algorithm of the second type. It was always correct, but with in certain cases it didn't terminate quite exactly, immediately, and it can go on forever. We can easily transform this algorithm into one that satisfies this definition for 1, so the ones that can return don't care. By exactly doing that, whenever we would have repeated the procedure, we return the question mark. And you can check that this is only with probability 1/4, so this is fine. And this also gives you a hint on how to realize the general transformation to prove the above theorems. Now there's quite a few other famous algorithms that can be called Las Vegas algorithms, namely randomized quicksort and quick select. So at this point in time, I should maybe comment on the difference between randomized quicksort and the average case of the deterministic quicksort method. These are often mixed up because the result is the same. So you know that, quicksort with a pivot chosen, say, at the first position in the subarray on random permutations, if this is your input model, then you get asymptotically 2n ln n comparisons. And this is the average case over all different inputs. So this is also a kind of expectation, but it's over the input. So Here you take E over the inputs, which also means if this assumption is not true, that you don't really have random permutations as your inputs, then the whole analysis is not valid. And you know, for example, if you pick really the first element as pivot in each step, then an already sorted list is actually a worst case for Quicksort, because we always have the smallest element as pivot. So this is actually fine for textbooks, but it's nothing that you should do in practice, picking the first one. You should do something slightly more clever, but I won't go into detail here. In theory, the best you can do to avoid this problem is to pick a random pivot. So in each step, you draw a random index P and then pick that element as pivot. Then the input doesn't matter. So we still get an average number of comparisons, an expected number of comparisons to n log n. But here we take the expectation over random choices of the algorithm. So over the random bits in our Turing machine, if you would like to stick to that. And this is really the important part. With a randomized algorithm, there's no worst case inputs. All inputs became average cases in the sense that we had it before. And you can take, you can destroy the possibility for a specific fixed worst case input by randomization. Now, having said that we're concerned with randomized quicksort and the same for quick select, we can view these as Las Vegas algorithms where they compute the function to sort the input or to rearrange the input so that we can pick a certain order statistic. And in that sense, they are always correct. They never return an incorrectly sorted list, or they never say, I don't know how to continue. And at the same time, they have a worst case guarantee on the running time. They never need more than a quadratic number of comparisons, and hence a quadratic number of steps on a reasonable machine. And what's interesting about these methods in practice is that the expected time is actually much better than this worst case guarantee that we have. So in this case, it was possible to fulfill both parts of this Las Vegas definition, always correct and a worst case time guarantee. But for other problems, this is not so easily possible. For yet other problems, it's not even possible to find a Las Vegas algorithm, or at least it doesn't seem like it is. So we would somehow be more generous and allow our algorithm to make errors. But if an algorithm can just return anything it likes, then that would just be not useful. We have to restrict a bit what we mean by that. And that's the definition of a Monte Carlo algorithm. Now these two, you know that Las Vegas and Monte Carlo are just cities with large casinos and are traditionally so. Now if you would like to have a cheap mnemonic for remembering which one is which, as an English-speaking person you might say, in Monte Carlo, the croupier will speak French, so you don't understand what he says, and you don't know whether you have won or not. Whereas in Las Vegas, you will understand what he says, hopefully. Therefore, Las Vegas is the easier location for you. Whether this helps you or not, I'll leave it up to your judgment. So what is a Monte Carlo algorithm formally? It's again such a randomized algorithm that computes a certain function, but in the following sense. It computes the correct result with a certain probability But for all other cases of the random computations, we don't make any restriction. So it can compute some other value of this output set gamma star. We could also allow the question mark again. So in a sense, Monte Carlo algorithms generalize on the Las Vegas algorithms. But all that we really require is that there's a certain guaranteed probability for the correct answer. And there's two slightly different variations. One where we require the existence of a global epsilon, so that for all inputs the probability guarantee is a bit over 1/2. Whereas in the unbounded error case, you could rewrite it in the above form where just the exists goes into here, right? So it looks like this is a small difference if you compare greater 1/2 to greater equal 1/2 plus some fixed epsilon. But it's actually that here epsilon can be a function of x, and that's, well, you may know other instances where exchanging the order of such two quantifiers makes a big difference. And it will also make a big difference here, as we will see probably next time. Before I can make precise why this is really such a big difference, we need again a bit more of probability background, but it will by far not be as abstract as last time. Rather, we will cover a few very helpful tools for proving things in about probabilities. And these are called tail bounds because they're of this shape. We bound the probability that a random variable is far away from something. So tail means if you draw the probability density function or probability mass function, then it often has a shape like this, where you have the expected value around here, and then the tail would be bounding the area under the curve on this in this direction. That's a tail bound of this part of this shape. We often have symmetric ones for the other part, and sometimes we even combine those, so we just define a neighborhood around the expectation. We'll come back to that a second later. A different term for a similar thing is concentration of measure, which means if we have a random variable that changes over time or with the input size, and it becomes ever more peakier around the expectation, then we speak of concentration. And the two often go hand in hand and are very helpful tools, so I promise. The first and mother of all these inequalities is Markov's inequality. And it's actually a very simple statement. We have any random variable. The only important restriction is that it must be greater or equal 0. So we will usually assume here that we are dealing with real random variables. Then the statement is, for any such constant, we have the probability that the random variable is larger is bounded by something that depends on the expectation of that random variable. Now let's quickly prove this before we go on. I will not prove all of the tools that we will cover in the lecture today, but I will at least prove the basic tools to give you a feeling for how this works, and also to put you in the position to customize these tools when that would be needed. But also the fact is that the proofs are very simple and a bit insightful, at least for the next two. So it's helpful to include them. Let's assume we have such a parameter a given, and let us, depending on this, define a random variable I, which is the indicator random variable for this event x greater or equal I, which if you like, you could write it with this Iverson bracket notation. So I will occasionally use this notation if I write something in square brackets and the thing inside is a condition. And I mean by this that it takes the value 0 or 1 if this condition is fulfilled and 0 otherwise. That's a very helpful convention that should definitely be widely accepted. It's not very widely accepted to use it for indicator events in stochastics. Somehow this got stuck. I'll use both. Okay, so we have a new random variable that only takes values in 0 and 1. So let's look at the two cases that are possible. If x is less than a or greater or equal a. In that case, I is 0, and here it is 1, that's for sure. And in that case, if x is greater or equal 1, we can also write x over a, which is also greater or equal 1 in this case, just because x is greater. And by that we see that in any case this equation holds, where we now use the value of this indicator variable. So in the second case, the result is already stated here. In the first case, we only have to show that these are greater or equal 0, and well, they are by definition. And here, this is where we use this assumption weakly positive. So it's really a vital assumption. So this holds in all cases, which also means that we can take the expected value on both sides. Let me start over here. Well, since this holds for all choices of x, so I is fully dependent on x, so the only thing that's really random in this statement is x. Now if we take the expectation here, since this is true for any specific value x can take, it's also true for the expectation because of linearity. Using linearity of the expectation again gives you already what we look at here. Well, and what's the expected value of I? Well, just going by the definition, the expected value of I is, if this is true, it's with value 1, so you have 1 times the probability for this plus 0 times the probability for not this, but that's 0. So it's nothing else but the probability for x greater or equal a. And that finishes the proof. This will be something that is, in general, something you could remember because it's often helpful to write probabilities as expectations of the indicator variable for that thing. This is not in itself not anything that helps, but you can then compute with this random variable that is the indicator one. And as in this case, this sometimes helps to make a statement that you could otherwise not express. I'd like to mention that this is the form where the proof is most streamlined, but we will actually find this form a bit nicer to use, and it's exactly equivalent. X is greater than some multiple times its expected value with a probability of 1 over a. This is the one that you should keep in mind, whereas the one above is to make the proof work. Now, because Markov's inequality is, oh, no, I'm at the wrong end of the whole document. There we are. I, of course, wanted a page after this one. Since Markov's inequality is so important and so basic, you will see that the others that we will show actually rely on it, even in the proof. I think it is helpful to have some way to remember it. And there's one that I found in the lecture notes of Jeff Erickson that is, I think, is helpful because it's graphic. This doesn't suffice to prove the general case, but as a mnemonic, it's definitely helpful. If we have a random variable that's actually integral, then there's another observation that's of general interest and applicability. Well, you know, the expectation is of the form n greater equals 0, n times the probability for x having that value. That's just by definition, and of course you can leave out the 0 if you like, but that's not the point. There's an alternative version for such random variables, where you also sum over all these. Well, let's leave it for symmetry. But now you only sum over the probability, but for x being at least n. That this is the same is actually just a reformulation of the sums, but it's something you can prove graphically quite easily. So let me try to see if I can do that. Assume you have a random variable that just takes on these 4 different values, and these are the probabilities. So this is x is this with the probability given by the height of this bar. Then the first way of the expectation just says this is the sum that you have to compute. I'm not telling you any secret. Now the second sum actually says I can rewrite this as such. So let's here draw the probability that x is at least 1. Well, actually x is one of these 4 numbers, so this is 1. Which, by the way, must be the sum of all these 4 heights. I hope this at least approximately checks out. Now the probability to be at least 2 is a bit smaller. And actually it's smaller exactly by p1, right? Because all others are greater or equal to 2. And if we continue like this, then with p2, so this should be a bit higher. The height p2 is lost in the next step. Then we lose a lot, p3. And actually we might need one more to make the point, so then it goes down to 0. And now the idea is just that instead of summing column-wise like here, you sum row-wise. And then, for example, this here is exactly the probability for for 4, which we multiplied by 4 over here, and you see that it's exactly added 4 times if we add up the sum group by greater equals. So this is a graphic proof that these 2 sums are really the same. So this is something That's another helpful formula that you should keep in mind whenever you have a random variable that only takes natural numbers as values. But I actually wanted to give you a mnemonic for Markov's inequality. And this is if you generalize this and draw a plot where you have A over here and the probability for x to be at least A. So this is exactly the plot that we had here. But for a general random variable of this kind, this will be some graph starting at 1, and then there will be certain steps where it drops, and you don't exactly know at which points it drops. That depends on the values, and by how much it drops depends on the probabilities. But in any case, if you fix some value for A, that will give you some value for p of x greater equal A, then just graphically speaking, by the shape of this function, because it always has to go down and it doesn't have slope, it's always horizontal and then jumps. That's just by definition of this probability when x is discrete. Now you know that this is actually the area probability of x greater equal A times A. Well, and this formula says if you sum over all the stripes, so actually the jumps must be at integer positions, so you can simply think about this being stripes like this, right? So then E of x is just summing up all of these. And since the red part always has to lie under the curve, you have proven that times A is at most this, and that's nothing but Markov's inequality. So I hope this helps you remember this helpful inequality, because you will find it helpful in many cases. Now let me add that Markov's inequality is not actually helpful in the pure form. It's often too weak. But since it has so little prerequisites and constraints, you can often apply it to a transformed random variable. So you take some function f of the random variable. So unless f is a non-measurable function, and we will not encounter those, then f of x is also a well-defined random variable. And if you find that this is also non-negative, then you can apply Markov's inequality to this function instead of x itself. And this might give you a much better bound if your function is chosen clever enough. And we'll see two examples of this improvements along this way. We need a definition, a notion that might be familiar to you, but let me repeat that. If we have a random variable, then we take the kth power and the expectation of that. This is called the kth moment of x. So the first moment is nothing but the expectation itself, and the second moment is closely related to the variance. So I included the definition for variance and standard deviation once more here, even though you probably know what this is. But the variance is just take x, subtract the first moment, the expectation. So if x before had some non-zero expectation, it's now shifted to have the mean at the origin at 0. And then you square what comes out. So what this means is that you amplify the differences, right? So if x used to be pretty close to 0, then squaring emphasizes this. If x was large, then squaring emphasizes this. And then the expectation over this gives you another number. And that's the variance. And if you take the square root of this, you get the standard deviation. And often this is, the standard deviation is often the more intuitive notion because it has the same kind of quantity, it's the same type of quantity as x is because you don't have these squares in. It has the same unit in the physical sense. Now, if we have such a random variable x where we can compute the expectation and the variance, I should say whenever we write this expectation here, we actually would like to imply that this exists, that the expectation is actually a sum or an integral, which might just not converge or might not exist. And in that case, it's not defined what the kth moment is or what variance and expectation are. So whenever we write these in formulas, we mean by that they exist and are finite. So if we have a random variable x, we can use the expectation and the variance to get a better bound than Markov's inequality, and this is called Chebychev's inequality. For any parameter a again, you can bound the probability that x is far away from its expectation in this sense. So you take the absolute value of the difference. And this is bounded by the variance and now the square of a. Recall that in Markov's inequality we had just over a here. Now we have the square. This is what makes the bound better. So let's again quickly prove this. And all we have to do is find the Markov hidden inside this formulation. And for that we rewrite the term that we have. So this is just the probability that we have here. Now in this inequality, both sides are positive. This is by definition, and a is by assumption. So the probability that this inequality holds remains the same if I square both sides. And let me just do that. Now the good thing about the square is that it amplifies differences. So here we had some random variable that had mean 0 because we just subtracted it. But it might be occasionally far away from 0 still. And if we square it, we emphasize that. Luckily, this here is again greater or equal 0, so we can apply Markov's inequality at this point. And as you see here, we get, instead of an a square. Now Markov's inequality says take the expected value of this. And that was just this term squared. And then divide by this, what we had here. Well, and now just by definition, which you see up here still, this is nothing but the variance of x. In a sense that the variance comes up here it's not a coincidence, but this is not what makes the bound strong. The point is that the variance exists We write it, so we mean that it exists. And that tells you something about how far away x is from 0. That's essentially the point. So let me write that down. The trick that we used here was that centering, subtracting the expectation. This operation is called centering. And taking powers, squares in this term, in this case, made the random variable under consideration more variable. Okay, I should set this like this. So if you have something that's far away from 0 and you square it, then this is amplified. And therefore you could afford to have a larger a, which gives you a larger denominator in the bound that Markov gives you. Okay. Let me just mention that you can find similar and stronger bounds if you don't just square here but take even higher powers. In that case, you will also get a higher power here, but in order to say something useful about this term here, you need to consider higher moments, and these are not so nicely expressed as the variance is in this case, and we will not need that generalization. But this is doable, so it's really a general technique that's called the method of moments. Now we can use Chebychev's inequality for a simple statement like this, which is really nothing but a corollary. I don't even intend to write down a proof, because it's just applying it in the very basic way. Let's assume we have a sequence of random variables. So we haven't encountered something like this before, so it's as usual. We have a sequence indexed by some subscript, and it's supposed to go on forever, and we want to say something about this in the limit. And we assume that the expectation variance exists for all n and satisfy this important inequality, if you like, namely that the standard deviation is strictly smaller than the expectation. And what this says is that the standard deviation is the right quantity to measure how variable a random variable is, how dispersed it is. And if this for large n is much smaller than the expectation, then you should expect that these x's are actually not random at all in the limit. And indeed this is the case in a certain sense, namely in convergence in probability. If we take x and divide it by e of x, I should add the n's here. And we assume that this, so this is just another sequence of random variables. And this converges in probability to the constant 1. And this phrase says nothing but what is written down here in this formula. For every epsilon, the probability to have a deviation of this term from its limit, its supposed limit, of more than epsilon goes to 0 as a function in n. That's what convergence in probability means. It's one of several notions of convergence for random variables. That's why we have to stress this here. There's a few others. A few are stronger, a few are stricter. So this one is a bit in between. but I think it's an intuitive one. It says that the probability for deviations goes to 0 in a pointwise sense. So I will not further comment on this, but I think this is something useful to keep in mind. Whenever the standard deviation is in the limit smaller than the expectation, then there's actually not much random about these things in the limit. Now in the general case, this is all you can do, and sometimes this is sufficient, but in many cases we will actually need much stronger concentration inequalities, and for a few specific distributions these are actually available and have commonly been referred to as Chernoff bounds. This is not one specific inequality, but a whole family of inequalities. And I will present one that's easy to prove and one that's helpful to use. And I hope that these two will be sufficient for all you encounter. We will, in the proof, again apply Markov's inequality, but to a function that's much stronger than taking squares. Maybe keep that in mind, because it will take us a few steps before we apply it. Now, what does Chernoff bound? What does the first Chernoff bound say? First, Poisson trials is an established term for the following model. You have random variables x1 to xn. Each of them is just a binary variable, a random bit if you like. And the probability for a 1 in each of these cases may depend on I. So this is important here, what makes the model a bit more general. If all pi are the same, then we speak of Bernoulli trials. So if you ever encounter one of these two terms, usually that's what's meant, same probabilities or different probabilities. And the quantity of interest is the sum of these n bits. So in case of Bernoulli trials, this is the well-known binomial distribution. And the second Chernoff bound will actually cover this case. But the first one will be for the more general Poisson trials. And in that case, we have, so mu is nothing but the expectation of x. I should have written that. Mu is often used for the expectation, for the mean. That's why it's called mu. So this is the sum of these p's, of the pi's. And then we have the following two bounds. I will prove this one, and this one follows from this by essentially just massaging this term a bit more, approximating functions in here and so on. So the second part is often easier to apply, and the first part is easier to prove. And I will leave out how to get from one to the other, because this is just rote calculations. And if you're interested in that, you can find that in textbooks. But for the basic part, I want to give you a proof, because it's again giving you insight into why exactly all these conditions are necessary. So for the proof, we assume an additional parameter t that's positive, and that's to be chosen later. So in the first part, we will show anything generic in t, and it will be valid for any value of t. Now, the probability that x is at least 1 plus delta times mu, that's just what's given here. We can again express this probability by transforming the parts on both sides of the inequality. And this time we take, instead of just squaring, we take e to the t times whatever was written here. And then we observe that this is again greater or equal 0. So, no surprise, we again apply Markov's inequality. Now that means take the expectation of the left-hand side and divide by whatever is on the right-hand side. Now we will just have to see how we can compute this. Okay, that will take us a bit, so I need another page. First of all, let's say we take this out because that will not change in a few steps. Now the expectation here involves x, which is nothing but the sum of the xi's. To make it more readable, I'll use x instead of e to make it a bit more readable. So the t we can pull directly into the sum, t times xi. So far I've just rewritten and inserted the definition of x. Now since this is an exponent and we sum up over here, we can split, we can pull the sum out and make it a product. Right. Now at this point, let me underline that once more. We assume that the xi's are mutually independent, which means the whole set, whenever I fix the probability for any of these, the probability for the joint event that they together take a certain value factors into the product of the individual xi's having their individual value. And a consequence of that is that also the expectation of a product of these xi's factors into the product of the expectations. And this is the reason why mutual independence here is really important. And something weaker like pairwise independence or so would not be sufficient. So because they are independent, we can pull out the product and take expectations individually. This is the key step that makes it sensible, makes it work, that we started with such a strong amplification of this inequality. Okay. Now these terms are actually relatively harmless because xi is a binary variable, so it can only ever take two different values. So we can compute this expectation by simply plugging in the two values that we have. So this can be 0 or it can be 1. If it's 1, then it is so with probability pi. And then the value is e to the t. And with probability 1 minus pi, it's 0, and then it means it's just 1. Right? Now, let's simplify that a bit. That's 1 plus pi. Then we have e to the t minus 1 from that part here. And now we use a famous inequality that is sometimes called the most useful inequality ever. I don't know whether I should agree. Maybe the one with the logarithm is also helpful. So this holds for all values of y. Let me give you again a quick graphical proof. So if you draw the function e to the y, it looks like this. And this is a convex function, which means it's curved like this. And whenever you take a tangent of this curve, so a line that touches the curve in exactly this point, then the function, a convex function, lies above all its tangents. That's something to write down maybe. And that's, I think in this graphical way, it's much easier to remember this. Well, and what is this? This is exactly the tangent at 0, because the value of the function at 0 is 1 and the slope is y. And also, and this is maybe an observation that you like most, this is actually the truncated Taylor series of this function e to the y around y equals 0. So this is nothing but the first order or second order approximation of this function locally around the point y equals 0. And that's okay. That's enough of a digression for this cute little and helpful inequality. So using this here, applying it on this, we find that we have this term that we copied over all the time, product, and then e to the y. Now you might think that this actually looks more scary, but because of the product, this nicely checks out. So the next step is to move the product in again. And it turns into a sum. And let me already pull out the common factor. Well, and then you see that the sum over the pi's, that's nothing but our mu, the expectation of x. So recall this was the term that I'm skipping here all the time. So what we have is e to the mu times this. And divide by the term that we had before. That was just this. Now up to this point, t was just some parameter, so this holds for all choices of t that are positive. And it seems like a good choice is, so in principle you can use this inequality and minimize over t. So you can take the smallest value of this term that you can find for t, and a good choice in minimizing is just taking the natural logarithm of 1 plus delta. Since delta is greater 0, this is also greater 0, so it's a valid t. And then we find that e to the t is simply 1 plus delta. So 1 plus delta minus 1, that just leaves the delta. And here we have the same, so we get a 1 plus delta as a basis, 1 plus delta mu, and now we have a common exponent mu that we can move out. Sorry, e to the delta, that's 1. And then the complete thing to the power of mu. And that was exactly, if you remember, that was exactly the first inequality. And as I said, I will not prove how to get to the second. This is just transforming this term a bit more. Instead, let's look at the most interesting special case. If we have the binomial distribution, so this means x is the sum of n such Bernoulli trials, and now each of these has the same p. Then we have a bound that's, for the one thing, it's a bit nicer, a term on the right-hand side, and the second change is that here we have a concentration inequality. We divide x by n, which is essentially a scaling so it's something like dividing by e to the x. It's just more conveniently written. So I mean, it's clear that the expectation of x is n times p. That's directly from this representation. So x divided by n should be around p, and so this is the expectation. If we subtract that, then the probability to be just a tiny delta above that is exponentially decreasing, where you even have delta squared inside of the exponential function. This is really a strong bound that allows you to show much tighter concentrated results than Markov or Chebychev. And as a not so trivial example, let's look at how much we can trust in Quicksort's good expected complexity. I've already said that essentially we have these 2 n log n comparisons on average, but up to n squared complexity in the worst case. And it would be very interesting to see how far away Quicksort is usually. To express that nicely, I'll use a somewhat sloppy, or maybe not sloppy, but a bit imprecise notion, but it's a very convenient one. And a bit like the big O notation, it got stuck because it's reducing the complexity of our statements. And that's the notion of with high probability statements. We say that an event that depends somehow on a parameter happens with high probability if for any c, the probability that this happens is essentially 1 with an error of n to the minus c. And this is really a strong assumption, because this says for every exponent, every fixed exponent, but every exponent as large as you would like, you can express this probability as such in the limit for n to infinity. And the second notion that's related is if we have a random variable that depends somehow on this parameter, we say it's in a certain O term with high probability, when, again, for every exponent in the error term, we find a constant that is essentially the constant in the O term, which means nothing more that this constant in the O term may depend on the c. It may not depend on n, of course, but it may depend on the c, so that the probability of that this variable is larger than predicted by this O term is again of the same shape as before. So both of these statements are very strong statements, very strict concentration results. And we will show that for Quicksort we can actually get such a statement. The cost of Quicksort is of the order of its expectation with high probability in this precise sense. What we will actually show is that the height of the recursion tree is logarithmic with high probability. And the second from that follows Now before we attack the proof, let me quickly say what I mean by recursion tree of Quicksort. So a run of Quicksort usually picks some pivot element, and then after partitioning, here are all small elements, here are the large elements, larger than this pivot. And then after partitioning, this one element has reached its final landing position in the sorted array. And we recursively continue in the left and right half, or left and right segment, not necessarily of the same size, and do the same again. So we'll find again some pivot here, continue, and so on. And as you might know, if you always associate with a certain partitioning step its pivot value, then what you get here is a binary search tree. Okay, let me say that again. The recursion tree of Quicksort, if you represent each partitioning step by the value of its pivot and connect it to its two recursive child calls on the left and right half, then what you get is a tree. And not only a tree, it's a binary search tree, because all elements on the left here have to be smaller than the pivot. That's just the invariant that we create by partitioning. So and as such, this tree has all the, okay, this goes on, right? It's not finished yet. This tree is a bona fide binary search tree, and it's a random one, because in randomized Quicksort, the position of this pivot in the list is random. So this random binary search tree has all the notions attached to it that any tree has, and in particular we can talk about the height of this tree, which is the length of the longest path. And if you go back to this picture, you see that on every level of the tree, we have at most n elements left. It might be fewer, because if a few of the calls already terminated, then here we will actually have strictly less than n. But up to here, except for the pivots also are lost, so we always have a few less than n except for the first one. We get exactly n. But that means if you bound the height by logarithmic, then you bound the total effort by linear arithmetic. Okay, let's see how we can at least start with this proof that Quicksort recursion trees have logarithmic height. We'll need a slight bit of notation. I use V for one of these nodes. So this could be a V, any node in the recursion tree. Then by n of V, that's the number of elements in the subtree of V. So if this was V, then that's n of V. Okay, just the size of the subarray that I partitioned in that step. And say J of V is the size of the left child. So in our case, for that, if that was V, maybe more explicit, then this here, that's n of V, and that's J of V. Okay, so the size of the left. And now we define a notion. We call a node balanced if the following holds. Well, either if the subtree size of this node is just a single element. In that case, it's balanced because we don't continue. Or this j divided by n, so the fraction of elements that went to the left, is bounded above and below, namely by 1/3 and 3/3, 1/4 and 3/4. I'm sorry. So what this means is that the split is never worse than 1 to 3, and symmetrically also, right? And this means that essentially our pivot must be in the middle half. This is roughly the idea. So let me write that down. In a balanced node, this reduces the subtree size of its children to at most 3/4 of its own size. Running from this, we get the following key observation. Any recursion tree for n elements can contain at most a certain number of balanced nodes, because they guarantee a certain reduction in subtree size. And you can think about it that this is the right size, so 1/n, which is, if you like, you can apply some logarithm rules, and this is at most 3.5 ln balanced nodes. And the reason is simple. After so many balanced nodes, the initial size of the tree can be at most n elements, is reduced so many times by at least this factor. And if we just write that down, then you know that this just cancels, so this is n, 1, sorry. And that means at the latest, after so many balanced nodes, there's nothing more to split. Okay, so this finished the proof for star. Now we are almost there. We would like to apply Chernoff's bound to the following random variables. If we follow a path in the tree, can go left and right, no matter. Then at some point we reach a leaf L. Then at each of these nodes, we can ask if that was a balanced partition. That's a 0 or 1 question. And we can show that a path of a certain length becomes unlikely if the number of balanced nodes must be below this. Now, in order to apply Chernoff's bound, we would need to assign here such indicator random variables. Say to the sum of these, okay. we need that these are mutually independent. If x is a binomially distributed random variable, this is just by definition so. But now we would like to construct x as a sum of these. So we need that these are mutually independent. And this is not the case if we ask whether the node is balanced. And why this is not the case and how to finish the proof still, despite this fact, this is what I will show you next time. Stay tuned.